Have you ever really thought about what's going on inside your computer? I mean, really thought about it? It's not magic, but it's the secret world of, well, organized chaos. So let's dive in and uncover the hidden life of something called a process. I mean, think about it for a second. You're playing a game, right? But you've also got a web browser open with like 20 tabs, and you're streaming music at the same time. How on earth does your computer handle all that without just completely freaking out? It feels like it shouldn't be possible, but it's all thanks to a really brilliant system of organization. All right, to solve this mystery, we have to meet the main character in our story, the process. This is that magic moment when a boring, lifeless set of instructions on your computer suddenly springs to life and actually starts doing work. Okay, let's think of it this way. A program is like a recipe book sitting on a shelf. It's just a list of instructions, nothing more. You've probably seen files that end in .exe on Windows or other types on Mac and Linux. Those are just the recipe cards, the static plans. But a process? That's you, in the kitchen, with flour on your face, actually cooking the recipe. It's the program in motion, the one actively getting the work done. Now, a process doesn't just sit still. It actually grows, kind of like a tree. It starts out as this tiny little seed. As it runs, it needs more memory. That's its trunk getting thicker. It takes on more tasks and it starts sprouting branches. But, and this is a big but, there's a danger. A nasty bug called a memory leak can make this tree grow completely out of control, hogging every last bit of your computer's resources until, bam, it all comes crashing down. So with all these living, growing processes running around, you can imagine things could get chaotic really, really fast. So who's in charge? Who makes sure they all play nicely together? Well, that brings us to the master manager of this entire operation. Meet the kernel. Seriously, think of the kernel as the master juggler at a circus. It's the absolute core of your operating system, and its entire job is to keep all of those process balls up in the air at the same time. It's the one that decides which process gets to use the computer's brain, the CPU, at any given millisecond, creating this perfect illusion that everything is happening all at once. Okay, here's a new puzzle for you. Your computer's CPU is unbelievably fast, but other parts, like your hard drive, they are painfully slow in comparison. So what happens when a process needs to grab some data from that slowpoke drive? Does the super-fast CPU just tap its fingers and wait? No way, the kernel is way too efficient for that. It does something amazing called a context switch. Think of the CPU as a clerk at the DMV. If you get to the front and realize you need to fill out a form, the clerk doesn't just stand there and watch you write. They yell, "Step out of line, please, next," and immediately start helping the next person. The CPU does the exact same thing. It instantly switches to another process instead of wasting a single precious moment. So we have the kernel juggling all these processes, switching between them at lightning speed. But how does it keep them from, crashing into each other and making a huge mess? The answer lies in a really clever separation of power. I want you to picture your computer's memory like a two-story building. Downstairs, in what we call user space, is where all your apps live. They each get their own little apartment. Your game, your browser, your music app, they're all neighbors down there. But upstairs, in kernel space, that's the building manager's office. This is where the powerful kernel lives, and it has full access to all the building's controls, all the hardware. And your apps, they can't just barge upstairs whenever they feel like it. And this is absolutely the most crucial part. Each process gets its own private protected apartment. The technical name for this is a virtual address space, but it's basically a clever trick that makes each program think it has all the memory in the entire building to itself. This prevents one misbehaving app from reaching into its neighbor's apartment and, breaking all their stuff. This separation is exactly what keeps a single crashing game from taking down your entire computer. So what happens if an app needs something from the powerful manager upstairs, like wanting to use the keyboard? Well, it can't go up there itself. Instead, it has to make a very formal, polite request called a system call. And how does the kernel know how to talk to all that hardware, like the keyboard or the mouse or your printer? It uses these special little translators called device drivers. Each driver is a tiny program that speaks the unique language of one specific piece of hardware, which allows the kernel to manage everything without a hitch. Okay, this whole system is brilliant, right? You've got separate floors for safety, formal requests, special drivers. It's amazing. But it doesn't come for free. There's a hidden cost to all of this safety and organization, and that cost is time. Let's just walk through a really common example. you're waiting for some data from the internet. First, that data arrives in the kernel's mailbox upstairs. Then, your app, which is stuck downstairs, has to make a system call to ask for its mail. The CPU then has to switch into its powerful kernel mode, go upstairs, copy the data, bring it all the way back downstairs to your app's apartment, and then switch back to regular user mode. Only then, after all that, can your app finally read the data. It's a whole dance for every little piece of information. Exactly. All of that switching, that context switching between user mode and kernel mode is expensive. Every single time it happens, the CPU has to carefully save everything it was doing, handle the new task, and then restore everything exactly as it was. It adds up. And that's why programmers work so hard to minimize these switches. The very system that keeps your computer so safe and stable also adds a tiny bit of overhead that slows things down.
So now we can finally see the whole picture. It's not magic at all. It's just this incredibly elegant, complex system of rules and compromises, all designed to get the most out of our machines by balancing safety with pure speed.
So when you put it all together, the big picture becomes pretty clear. Processes are just programs that are actually doing work. The kernel is that master juggler, using device drivers to talk to all the hardware. The separation of user and kernel space is what keeps everything safe. And system calls are the official, polite way for an app to ask for help. And maybe most importantly, this entire beautiful system is a constant balancing act between raw speed and rock-solid safety. And that, right there, really is the ultimate takeaway. This constant balancing act between performance and security, between simplicity and power, that isn't a flaw in the system. It's a core design principle. It's not a bug, it's a feature. And deciding where to draw that line is what great engineering is all about. So next time you see your computer doing a million things at once, you'll know the secret. It's not magic. It's just a beautifully choreographed dance of trade-offs.